Come with me on a journey through space and time. Our universe is a vast and wondrous place filled with objects of unimaginable size and power. Imagine a spot in space so heavy, so dense that nothing can escape its pull. Not even light, the fastest thing we know. We call this a black hole. It's not really a hole, but a huge amount of matter squeezed into an incredibly tiny area. This creates a gravitational pull so strong it acts like a cosmic vacuum cleaner, pulling in anything that wanders too close to its edge. It is a one-way trip into darkness, a place where the familiar laws of physics begin to break down in ways we are still trying to comprehend. Now, let's picture something else, something equally magnificent. Imagine a star, but not just any star like our sun. Think bigger, much, much bigger. We call these giant stars megastars. These are the true heavyweights of the cosmos, shining hundreds or even thousands of times brighter than our own star. They are colossal factories of light and heat, burning through their fuel at a furious pace. They are born from enormous clouds of gas and dust, and for millions of years, they dominate their corner of the galaxy. These megastars are so large that if one were to replace our sun, it would swallow up the orbits of many planets in our solar system. These two cosmic titans, the black hole and the megastar, usually exist far apart from each other. They each follow their own paths through the grand ballet of the galaxy. A black hole might silently drift through the darkness, its presence only known by the way it bends the light of stars behind it. A megastar, on the other hand, blazes with incredible energy, a beacon visible across vast distances of space. For most of their lives, their stories never intersect. They are like two giants living in different parts of a cosmic kingdom, each reigning over their own domain, unaware of the dramatic encounter that fate might have in store for them. But our universe is a dynamic, ever-changing place. Galaxies move, stars orbit, and sometimes paths cross in the most dramatic ways imaginable. What happens when a wandering megastar, one of the brightest and biggest objects in the universe, gets a little too close to a black hole, one of the darkest and most mysterious? It's a setup for one of the most spectacular and violent events the cosmos has to offer. This isn't just a simple collision. It's a battle between two of nature's most extreme creations, a cosmic spectacle of immense proportions that can teach us so much about the universe we inhabit. Imagine our megastar, journeying peacefully through its galaxy for millions of years. It's so big and powerful, it seems like nothing could ever harm it. But space is not empty. It's a cosmic dance floor where everything is constantly moving, pulled by the invisible force of gravity. The megastar's path might slowly, over a very long time, drift toward the neighborhood of a supermassive black hole. At first, the star wouldn't notice a thing. It would continue to shine brightly, its immense gravity holding it together in a stable, spherical shape as it has always done, completely unaware of the looming danger ahead. As the star gets closer, the black hole's gravity begins to take hold. It's like a gentle tug at first, a slight pull that alters the star's course. This pull gets stronger and stronger with every mile the star travels closer. The black hole's gravity is not uniform. It pulls more forcefully on the side of the star that is nearer to it. This difference in gravitational pull from one side of the star to the other is what scientists call a tidal force. It's the same kind of force that causes the tides in Earth's oceans, but on an unbelievably more powerful and destructive scale. The star is being stretched. This gravitational dance becomes more intense. The star, once a perfect sphere, starts to get distorted. It begins to stretch out, looking more like an egg or a teardrop, with its pointed end aimed directly at the black hole. The star is now caught in a gravitational trap from which there is no escape. It begins to orbit the black hole faster and faster, spiraling inward like water going down a drain. All the while, the tidal forces are getting stronger, pulling and kneading the star, testing the limits of its own gravity that desperately tries to hold it all together in one piece. The star's fate is sealed. It has crossed a point of no return known as the tidal disruption radius. This is the boundary where the black hole's stretching force becomes stronger than the star's own gravity. The star can no longer hold itself together. It is at this moment that the process of destruction begins in earnest. The cosmic giant, a star that had shone brilliantly for eons, is now at the mercy of the black hole's immense power. The stage is set for a truly cataclysmic event, a process of shredding that will tear the star apart piece by piece in a magnificent display of cosmic physics. The moment the megastar crosses that invisible line, the shredding begins. The immense tidal forces from the black hole act like a cosmic cheese grater, peeling away the star's outer layers of gas. The side of the star closer to the black hole is pulled with so much more force than the far side that the star is literally ripped apart. It's not an explosion in the traditional sense, but a slow and complete unraveling. Streams of stellar gas, superheated to millions of degrees, are torn from the star's body. These streams are like fiery cosmic noodles, some of the longest and fastest structures in the universe. Imagine these streams of star stuff, each containing the mass of many planets, being pulled into a long, spiraling ribbon around the black hole. This process is called spaghettification, a fun name for a terrifying process. The star ceases to be a star. It is transformed into a disk of incredibly hot, glowing gas and dust swirling around the black hole's event horizon, the point of no return. This rotating disk is called an accretion disk. It glows with incredible intensity, brighter than entire galaxies, as the material within it rubs together, creating immense friction and heat before it finally falls into the black hole. Not all of the star's material falls directly into the black hole. About half of the shredded star, the part that was a little farther away, gets flung out into space at incredible speeds. This material is ejected in a massive, expanding cloud, a final testament to the star that once was. This ejected debris travels outward, carrying with it the heavy elements that were forged inside the star's core over millions of years. So, while the black hole gets a massive meal, it's also a messy eater, spraying the contents of its victim across the cosmos, seeding the surrounding space with the building blocks for future stars and planets. The feeding frenzy of the black hole is what creates the cosmic explosion. As the stellar material from the accretion disk rains down onto the black hole, it releases a tremendous amount of energy. This isn't just visible light. It's a brilliant flash across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. This event, known as a tidal disruption event, or TDE, is one of the most luminous and energetic phenomena in the universe. For a few months, this single event can outshine all the billions of stars in its own galaxy combined, announcing the death of a star to anyone watching from afar. So why do we, here on our small blue planet, care so much about these distant, violent events? It's because these cosmic explosions are like giant laboratories. They allow us to study the physics of extreme environments that we could never hope to create on Earth. When a black hole shreds a star, it gives us a rare glimpse into the properties of the black hole itself. By studying the light from the explosion, the TDE, we can measure the black hole's mass and even how fast it's spinning. It's like seeing the shadow of a monster illuminated by a final, brilliant flash of light. These explosions from shredded megastars are also special because they are incredibly bright. They act like cosmic lighthouses shining from the farthest reaches of the universe. Because light takes time to travel, when we see an explosion that happened billions of light years away, we are also looking billions of years back in time. This allows us to probe the early universe. We can study what galaxies were like when they were young, and how the very first supermassive black holes grew to such enormous sizes. Each new TDE we discover is another clue to solving the grand puzzle of cosmic history. Furthermore, studying how the star is torn apart tells us a lot about stars themselves. Megastars are rare, and they live fast and die young, so they are difficult to study. Seeing one get shredded by a black hole is like putting it under a cosmic microscope. We can analyze the different elements in the debris that gets flung out into space. This helps us understand how stars create heavy elements, the very elements that make up planets and even us. The calcium in our bones and the iron in our blood were forged in the hearts of stars long ago, and events like these help spread those vital ingredients across the universe. In the end, every time we point our telescopes to witness one of these celestial fireworks, we learn something new. We are explorers on a grand voyage of discovery. These events remind us that the universe is not a quiet, static place. It's active, dynamic, and sometimes incredibly violent. By studying the death of a giant star, we learn more about the fundamental forces that govern everything. We piece together the story of our cosmic origins and our place in the universe. And that is the greatest adventure of all, the quest for knowledge, written in the light of exploding stars.